So this equation 3, as you saw here, so that remains the after the for all the values n greater than or equal to 0, this is neglected. Well, more than one event, the for each n value for this p, this is true for, that means this is valid for n greater than or equal to 1, means this is true for p1 d by dt p1 t, d by dt p2 t, d by dt p3 t, and so on. For 0 event, let us see. So if the number of events are 0 up to time t plus h, that is p n t plus h equal to 0. That means p is 0 up to time t and no event. So that means if there are here 0, let me draw again maybe here. So p, this is t plus h. So number of events 0. That means probability of having 0 here and no events. That's the only option. Because if already p1 0 and there is no 0, one event is gone, eliminated, is not, that such probability is not there in this counting process. So p0. That's why again divide by h and taking the derivative, I mean the limit as h goes is 0. D by dt p0 t minus lambda p0 t order of h. So combining these two, so what we'll do is, we'll use the generating functions. So recollect two equations. Yeah, equation 3. This is one differential equation. This is another differential equation. So these two differential equations we combine together and then we solve using the generating functions. We solve using the generating functions, the probability generating function. Recollect that yesterday in lecture, GST is defined as generating function, which is summation n equal to 0 to infinity Sn p n t. It was yesterday used the notation an. Using Taylor expansion, we now take the derivative for that. Derivative for the this is generating function. D by dt of GST is d by dt of this term, and then that d by dt can be, if you expand it, Sn d s power 0, that is 1, d by dt p0 t s p1t d by dt and so on. So that way you can bring the d by dt inside. So the summation n equal to 0 to infinity Sn d by dt pnt. Just bringing d by d derivative, just bringing the derivative inside the summation. And this is from our yesterday's lecture. Yesterday we defined the generating functions. You all have the notes. Now, the same thing, this d by dt, we use that. So the equation 3 you saw for n greater than or equal to 1, this one, sorry. Yeah, this equation, you multiply by s power n. Why you suddenly we multiply that? Because we know that the left-hand side, d by dt s power n p n t is a term, is a one term in the definition of the generating function. And then taking the derivative d by dt. Because that thing is there, we try to exploit that association of Sn and p and t, and then we multiply that Snt for this equation. Snt, you multiply here Snt and so on. Similarly, we do the thing for multiply by s power 0 for here. Later you'll see. Combining these two together. Yeah. So you multiply equation 3 by Sn and summing over n equal to 1 to infinity, that equation there, recollect there, s power n d by dt minus lambda so and so plus lambda. And then similarly, equation 5. Equation 5 has only one 1 d by dt only one term, so we just need to, we don't have to sum up anything because n equal to 0 term, n equal to 0 part, that is, so we don't have to sum up. So these two together, so they're combining these two equations, 8 and 9, d by dt, the 8 and together, the summation is changed here, see, n equal to 1 to infinity, and this together it becomes n equal to 0 to infinity. So left hand side is nothing but the definition d by dt GST, and right hand side, if you see that this is minus lambda times, again this is GST. This is lambda times lambda, and then if there is Sn Pn minus 1, but that the form we need require is Sn Pn minus 1, Sn Pn, or Sn minus 1 Pn minus 1. Sn minus 1 Pn minus 1. So here, if you see this, note this term, we need s power n Pn, s power n Pn t. But here you see Pn minus 1, n minus 1 t. So what we do is here, to make it s power n minus 1, you multiply by s. So this is equal to s times Sn minus 1 P n minus 1 t. Yeah, we have this term here, Pn minus Sn. So Sn you multiply by s and divide by s. So if you multiply by s, divide by s, this becomes s power n minus 1. So this now Sn minus s power n minus 1 Pn minus 1 t, again in the GST form. So this is, if you take s out, this becomes lambda s GST. Lambda s GST. So that this becomes a d by dt GST equal to minus lambda s GST plus lambda s GST. So this is d by dt GST become lambda g. So lambda GST is a common term. So lambda GST s minus 1, or minus lambda GST 1 minus s, both are same. So this is a d by dt GST equal to lambda g s comma t s minus 1 is a differential equation. And we know that this kind of elementary differential equation we solve by variable separable method. So what we do is you bring the GST on the left hand side. So 1 by GST d by dt. These steps are in fact not needed for, not needed means you all know it, just a recap only. So bring the
T
next
is
step.
missing, I think.
Sorry?
T is missing in the last equation, I think. In the right hand side of last equation.
Oh yeah, there's a typo, you're right. I'll put it there. Thank you. So before I come there, I want to show that differential equation. So this equation further, this implies bring the variable 1 by GS, you bring the GST other side, GS comma T d by dt GST equal to right hand side lambda s minus 1. Yeah. So you take the derivative, now if you integrate this one, this is a derivative of that. So this is log GST, this simply log GST is e to the power of lambda t st, and then taking the integral with the constant term, you ignore that becomes e power lambda t st. So solution. So obviously you see that it is exponential form. So this indicates what? GST equal to e power lambda t s by s minus 1. So this is again e power lambda t s minus 1 is nothing but the probability generating function of Poisson distribution. Poisson distribution e power lambda t power n by n factorial, we saw the probability generating function of Poisson distribution is same as the probability generating function of the counting process. This is all the previous slides. All this is the counting process, isn't it? These are all things what we have learned is derived from the counting process. We didn't touch anything from the Poisson. But this is actually, we arrived at a functional form e power lambda t s minus 1, which is a generating function of the Poisson distribution. So two generating functions are same, identical means two probability density functions also same. So the counting process's probability generating function is same as the Poisson distribution's probability generating function. That part I'm not showing because that you can, from the undergrad lectures, you can verify, all of you. So counting process follows. Counting process is a Poisson process. That's what we learned. And then the thing you all focus, what you need to focus is how did we use the probability generating function in this derivation in solving the differential equation. That's the training part is, how did we use the generating functions. So a quick recap if you all want, we took the counting process, we defined the properties of the counting process, and then we wanted to show that the Pn is a Poisson process parameter lambda t. This Pnt is given like that. Then we showed that given the counting process with all the three properties, this is nothing but the Poisson process. Yeah. If you see an example, for T1 be the interval. So we discussed already several times during this particular slide, this particular example of counting process. E power p T1 greater than t, nothing but probability nt equal to 0. See the notation, tricky notation here. Probability T1 be the time at the first event. T1 be the time for first event, say first sixer. So all of you carefully follow this notation. What's here is interesting notation. With this kind of notation, you can use it various places in the books or anywhere you pick up any book or any article. This kind of notation will be there. So T1 greater than T means first event occurred beyond T. First event of interest occurred beyond T. T1 be the time at the first event. That means first sixer occurred, say, 15th over. T1, or first time the COVID patient with hypertension came after 3 weeks after clinic started. 3 weeks after that, you got the first COVID patient with hypertension. You are counting. Now, first event occurred beyond T means number of events at T is 0. These two are same. The meaning is first event occurred more than T means NT equal to 0. Is it clear to everyone, this notation? This the concept conceptually. And NT equal to 0 means you substitute in the previous that thing, the e power minus lambda t power 0 by 0 factorial, that is e power minus lambda t. That means T1 greater than T equal to this implies 1 minus T1 greater than T is nothing but probability T1 less than or equal to T. That is 1 minus e power minus lambda t. Maybe I should write down this one here. This means here, see, probability T1 greater than T plus probability T1 less than or equal to T. isn't it? Only two events, two possibilities are there. There is no other possibility. First event could occur beyond T. Say T is say third day of the clinic. You started a COVID clinic in the hospital. First COVID patient with hypertension came after third day. Is same as that means the first day and second day at time T, no COVID patient came. So probability T1 greater than T and T1 less than or equal to T. That means first event occurring T or below T. Sum of this will be 1. That's the law of total probability. If this thing is not clear, please stop me here and ask me. Not a problem. But this is how we need to compute the various things. Probability T1 greater than T plus probability T1 less than or equal to T equal to 1. That's why when probability greater than T is probability NT equal to 0, which is equal to e power minus lambda T. This is probability T1 less than or equal to T obtained as 1 minus e power minus lambda T, just 1 minus of that. And then I use it generalized. Instead of one event, more than, and Tn plus 1 means stands for n time for n plus 1th event. T1 be the first event, Tn plus n plus 1th event. So I skip it, and when I share the slides with you, you try to see how the generalized notation works as a homework, as a non-credit homework. Now let us understand what is a stationary process. And then once just a quick what we are going to discuss is stationary process increments, and then we're going to discuss the Markov property. We're going to soon come to the Markov property, and then we discuss the Markov results. And then today we're going to cover the simple two examples of the blood pressure and the random walk, and then we'll coin tossing examples, and then we clinical example of the how to obtain the infertility status of a woman using the Markov chain. So with that we stop today. So let me start the stationary process. Just a quick trailer what we are going to learn in the next few slides. So stochastic process, as we all know what is a stochastic process, a collection of random variables, and this collection of 1 minute. Are you able to see everyone? The slides are seen?
Yes, sir.
This, can you see the slides?
Yes, visible.
Okay, sure. I thought the link got disconnected. Yeah, a stochastic process is said to be stationary process or strictly stationary if the joint distribution of x1, x2, xn and xt1, xt2, xtn are identical for all the 1, 2, 3 for all these events in J. I will explain. This looks complicated, but so easy. So easy in the sense, which all you know already from this, all the questions what I see from you all, you are understood. Stationary, the name itself suggests that stationary means something that doesn't change. Stationary orbits, in the physics you understand stationarity. So stationary means something doesn't change. So similarly, the random collection of random variables is known as stochastic process. Yesterday we learned the joint distribution of x1, x2, xn, jointly happening of occurrence of all these events. Distribution of x1, x2, xn together, and the joint distribution of xt1, x1, xt1 after t plus 1 units, t plus 2 units, and so on, t plus n units. The joint distribution of these and joint distribution of these are identical. Then we call a stochastic process, that is xn is a stochastic process, xn n equal to 1 to infinity. That is a stochastic process if x1, x joint distribution of this and joint distribution of these two are identical for all. Then we say it's a Stationary process, that means the stochastic process does not change with time. That's the meaning of the stationary process. I think before we will see some examples. So this process weak stationary
Excuse me, sir.
when the mean of the process is constant. When you compute the mean,
Excuse me, sir.
mean is that statistics part we are not touching here. We are only this course is about the stochastic nature. So how to compute the mean, other things from from the other courses, other things in expectation of the xn. So the mean is constant and and the covariance of the process is CST. Covariance, how to compute covariance also you all know that, I'm presuming. So expectation of xs minus expectation of xs minus exs, xt minus ext. This is a covariance. And the covariance depends only on the difference of the time difference. Just for understanding, the summary is that such processes which are identical to the after joint distributions, when you change after some time, the joint distribution, when you change the time and still compute the joint distribution, x1, x2, xn, xt1, xt plus 1, xt plus 2, and xt plus 1 are identical. That's called stationary process. And then the mean is constant and covariance of the processes depends only on the difference. And increment, similarly, the increment, the name itself, increment suggests, so nothing to get all worried. Increment is, xu, you all so far clearly understood. From your interaction, I could see that you understood the notation xu. Xu means random variable at time u and random variable at time t plus u. The difference, if you take it, that's called increment, the value, the change in the value. Increment changes, which is the value, the increment of a process is the amount by which the value changes over a period of time. What is the increment of the value? If it is numerical, we are computing like a blood pressure example, the increment, the change, that's called increment. So a process is independent increments. If the increment is independent of the process excess, that means each time the changes, like number of cars you're counting, the change in the number of cars in a certain interval is not dependent on the number of cars in the past intervals. That becomes independent. And we cannot directly relate this kind of examples for the blood pressure because the value of the blood pressure is obviously dependent on the future values, or the similarly for the other things, other culture values, or other the lab culture, other things in the laboratory experiments. Maybe the past values are always dependent. So this is called increment. These technical terms we'll use because why I suddenly defined stationarity and the increments is we are going to use those things in the future examples. Xt equal log xt. This kind of a function xt equal log xt. This is independent increments. Let us define Markov property. Let S equal to state space. So state space is given. So that's why I use small notation, smaller x. This is a state space. Like I comma j. Yesterday you saw ij. Now we have x, x1, x2. They are all the states within a state space. S is a state space. These are all states. A process xn with the following property is known as Markov property. Let us see what is the property. Xn plus 1 equal to xn plus 1. This value. X1 is x1. X2 is x2. Xn is xn. Pxn, if this is equal to probability of xn plus 1 equal xn plus 1, xn equal to xn is known as Markov property. Actually, this x is not needed. I will delete it because it is that state is not used. When I correct the slide, there's a typo there. I will delete it. So xn plus 1 equal to xn plus 1, x1 equal to x1, x2 equal to x2. The probability is that this is a problem. Xn plus 1 and given the joint distribution. depends only on the last value, nth time step. The value taken by the random variable at the nth time step only determines the probability, the transition from xn to xn plus 1. This is a transition. You see, xn to xn plus 1 transition occurred. Now x1 took value of x1, x2 took x2, x3, x3, and so on, xn equal to xn. This entire probability becomes the smaller probability that only one conditional value, that's a recent time step. If such property holds, so we say xn, the process, the stochastic process xn follows Markov property. The Markov is the name of the person who suggested this property. This is known as Markov property. So Markov property means, there is notation, as I mentioned yesterday, this probability xn equal to ij, that notation is very important. That means probability that xn plus 1 equal to xn plus 1, some value, any state. So these need not be always fixed. You can take any value here, any value which is in the state space. Let me delete that for the. Oops. So in general, when A is subset of some combination of the states, if you consider xn plus 1 belongs to A, given all these individual random variable values, xn plus 1 xn plus 1 belongs to A is only depend on the recent value. Let us take example of yesterday's example of the coin tossing example. Or they're going into the in a building and then taking the steps. So after the 9 steps, after an individual reaches, after tossing a coin, the individual reaches a certain location in a room, in a building, at the 10th step of the 10th toss of a coin, x10. That location only depends on the previous step. There's a notation wise. If it is not clear, feel free to stop me as you all doing rightly. And then this is arbitrary. You don't have to xn plus 1 always. Need not take anything, any value in the state space. Xn plus 1 fixed. That means n plus 1 time step, whatever the value it picks, it depends only on the previous step value. That it's called a Markov property. Any process independent increments the Markov property that I'm skipping, and I would like to give you this is the home slide. I will be sharing it, and you all can verify yourself. This is like a homework, non-complete homework. Let us understand the random walk. Suppose random walk already you have some idea, given the examples and other things we discussed. Suppose xn be a random variable on an integer lattice at time. Integer lattice means integer numbers is 0 and on the number line. And xn equal to 1. That means nth step, the value is 1. And xn plus 1 is defined as xn plus 1 with probability p. Xn is 1 value in the number line 0, 1, 2, 3, 4. The number line is given to you. You can have -1, -2 also. If you want, you can consider that as total integer line. -1, -2, -3, and so on. 0, 1, 2, 3, and so on. And then xn plus 1 is defined as xn plus 1 takes xn value plus 1 with the probability p or xn value at xn nth step minus 1. So xn plus nth step, value of the random variable at n plus 1th step is equal to value of the random variable at nth step plus integer 1 with a probability p, value of the random variable at nth step minus 1 with a probability q. That's how we define random walk. Then x is a Markov chain. So same example in the room, in the building, actually someone write this random walk. Yes, this is the random walk. This is a generic example. Many such examples can be constructed. Random walk. That means you start at a one. So xn some value initially 1. So if this is xn, or say let us start with x0 equal to 1. Then x1 will be equal to either 0 or 1. Either 0 or 2. Start with x0 equal to 1 integer lattice. At the beginning, it is x0 equal to 1. At the first time step, it will be.
And what is lattice here? What it will represent?
-1, -2, -1, 0, 1, 2, so on. Integer, integer. This is integer line.
Okay, and it has nothing to do with that lattice we used to study in mathematics, wherein every tuple has to be a join and limit kind of a thing.
No, integer lattice. All integer values we are considering here.
So
Integer line.
my query is about this term lattice. So what this lattice here is?
Here in this example, only the integer line. You can consider the integer line without any real line. It is not only integer values line.
Okay. Right.
Integer values line.
Right.
One can consider real line also. That's not a problem. But in this case, I consider -2, -1, 0, 1, 2, and so on.
Because we used to study lattice as a poset, wherein for every pair of the element we do have a join and a meet kind of thing.
Correct. Yeah, integer lattice, that comes down to when you consider integer line, that comes to that definition only. But if you consider a mesh, 2 by 2 lattice, so when even the random walks are studied on this kind of lattices also. So an individual stands here. Next step, you take a right. If the individual stands here, it goes to right. Flip a coin heads, you go here. Flip a coin tail, you go come here, or you're gonna another direction, go from here. On a mesh, you can keep on traveling. That's an example. Another random walks can be constructed in any kinds of lattices, mesh or in any 3-dimensional objects, or you can go in a Euclidean cube.
Okay, right.
So x0 equal to 1 and x1 equal to 0. So next time step, it will be either 0 to go with 1 to 0 transition with the probability q, or 1 to 2 with the probability p. That's what I got definition with xn plus 1 with the probability p, xn minus 1 with the probability q. And again x2 could be, if it reaches 1, x2 could be 1 to, if it reaches 2, x2 could be 2 to 3 or 2 to 1 again. Or if it reaches 0, x2 is 0, the next x1 is 0, x2 could be 0 to 1 or 0 to -1, and so on. then such process is also Markov. That such process Xn is a Markov chain or Markov. It holds a Markov property. When we say discretely, we define that as a Markov chain. So this again, the Xn is a stochastic process with a discrete time, discrete space. The space is here what? Space of integers. All the integers, integer line. That's a space. And each integer is a state. Each integer is a state here. So understanding random walks is one of the important aspects of the stochastic processes.
So, what's the reason behind observing this Markov property? Conditional independence of the events, or what?
Yeah, even if there are that means your joint distribution. What happened is in the previous slide, if you see that the joint distribution of these all events, they are all simplified into one event.
And how can this happen?
No, it's not how can it is if such thing happen, then it's called a Markov property. As we saw in the example of the, we are not saying this is happening. If a process which is such property is known as Markov property, and then in a random walk example, you see that the location, the position of the x2 depends only on the position of the x1, not on the position of the x0.
Yes, correct. History is not history doesn't matter here.
Only one step matters.
Only one step matters, right?
Probability x2 equal to some value here, I or j, depends on x1, x0. This x0 equal to I, comma, x1 equal to k. This is equal to probability that x2 equal to j given x1 equal to k.
Yes.
This holds.
Sir, means a recursive process defines Markov chain.
Only when the recursive process only depends on the last term, only one previous term only determines the next value, not the previous all the previous values. So whatever the value of x0 is not decided for the location of x2. Location of x2, as I explained here, x0 equal to 1. You start with start the process with x0 equal to 1 initial value, and the next value it could be 0 or 2.
But sir, indirectly x2 is dependent upon x node also, because x1 is dependent on x node and x2 is dependent on x1.
Correct. They're all dependent, but the value of the x2 value depends only on x1, not x0.
Okay.
Because x2, when you x2 in this example, that's what I'm explaining, is x1 equal to, suppose it reaches x1 equal to 0. x1 equal to 0, that means x2 what? x2 could go to -1 or 1.
Okay, sir. Okay, got it.
Good, yeah, thank you.
So
That's why a simple random walk is a.
Yeah. So does it have any relation to that naive assumption in that naive base?
Sorry.
So I mean, when I saw this Markov property for the first time in this slide, so I was having an impression that as if this seems similar to the naive assumption in the naive base. So does
correct? Yeah, exactly. Yeah, this is the first naive thing came later.
Okay.
Like a Turing machines, many things are there. There are also Markov properties, Markov chains. Alan Turing, Turing properties we study. So that the Turing machines, they depend only on the previous step, not on the so many steps before.
But in Turing, a kind of memory is involved in terms of the left and the right movement. So
Correct.
yes,
Like
yes.
maybe transporting on a road, a two-way road, once we have adopted one road, then
Correct. Exactly. Like, sorry, what happened? You all can see my slides. Can you all see the slide?
Yes, yes, visible, visible.
Okay. Yeah. Like that. Those examples, the Turing, some kind of Turing machines, and as you say, that even signal problems, signaling light signals in the roadways. There are many simplifications of the random walk. In in general, we can adopt random walk situations for various things in our real world. And they all, when we can't relate to this random walk, we'll also study the gamblers model, but that's out of scope here, because gamblers model means any person goes to the gambling area to play the gambling, and then gambler, because you all know that the story of probability. The Andrei Kolmogorov in the Russian probabilist, he started. I mean, the idea of he was a gambler. I mean, gambler, he used to play a lot of gambling things in the gambling places, and then he used to love the card games and the dice. All that they all related to the gambling. That's why the probability examples, they start with the die, and then the cards, playing cards, all these things. Because the Kolmogorov, when he started, he used to give all these examples, and he was a gambler. And Andrei Kolmogorov, when he started, the idea was, when a gambler goes to the gambling arena with so in the pocket, you keep some, say 10 rupees, you keep it in the pocket and go and play. Each time you win a game, you get 1 rupee. You get 10 rupees to 1 more rupee, 11 rupees. And then you lose a game, you lose 1 rupee. That means you become 9, you will have 9 rupees in your pocket. And the gambler come back to home. Whenever no more rupees to play, gambler quits the gaming center or gambling center, come back. So that's called gambler. Most of the time, gamblers ruin their life. That's why it's called gamblers ruin model. You see examples on lottery tickets. Lottery tickets. Most people buy the lottery tickets, but very few examples of winners. Most people lose the money in the lottery. So that's a gamblers ruin model, also a Markov chain. So these kind of examples can be simple random walk can be extended to various other places, various other situations. So we'll touch base on such examples later. Let us see this example of blood pressure in terms of the XN. Suppose XN be a random variable describing the value of the blood pressure of a person measured over a time period. XN is a obviously stochastic process, because XN is a random variable describing the value of a blood pressure measured over a time period. So it is measured over a time period. Various values of XN are a stochastic process. So XN is suppose defined as, in a simplistic way, XN is defined as Cn by Dn, where Cn is the value of the systolic blood pressure, Dn is the value of the diastolic blood pressure.
प्लेन वो गया
Xn equal to Cn by Dn, mm plus Hg, hemoglobin, millimeters plus hemoglobin. That's how they define Xn equal to, suppose we define Cn by Dn mmHg, where Cn is the value of the systolic blood pressure and Dn is the value of the diastolic blood pressure. So this kind of example, Xn, this exam is Xn. If you define specifically like that, Xn is a Markov chain. If you define, because each value, the value would not jump. It has to depend on the previous value, and so on. If it's increasing and decreasing, the value of the random variable depends only on the previous value. So this is just this example is only repurposed for the sake of fitting the Markov chain. So xn cn by dn is a example for a Markov chain where the xn is a value of the blood pressure of a person measured over a time period. Now again, Markov chain can be treated. This Markov chain, the value you saw previously, can be treated as a sequence of random variables. Sequence. So this is just not an English sequence here. The sequence here means it's a mathematical sequence. So sequence is in general, sequence is a real valued function whose domain is a natural number set. So that's why it's a sequence here. So if you so let us instead of xn, so in general math, we define sequence an is a sequence for all values of n. You can say you can start from 0 or you can start from our choice, 1, 2, and so on. But n greater than 1, when you write this n is an integer, but n belongs to n in natural number set, whereas an is a real number. This an is a real number. So sequence is a real valued function whose domain is a natural number set. Similarly, here the sequence here, Markov chain treated as sequence of random variables. x1, that's why you see that these values x0, x1, and so on, x0, so far you see that we are not defined random variable with a real valued suffix. Unless it is a continuous time with intervals. Time steps usually we here discretely we defined as x0, x1, x2, and so on. So that's why yesterday someone asked the question about the continuous time interval, the value. Yes, it can consider any values 99.9 or 91, the row value. Yes, one can, the way we define. If we define interval, state as an interval, then one interval to another interval. Jump from one interval to another interval. If we define state as a one particular number, then one number to another number or one state to other state, head and tail. If you define the state as an interval, like a temperature between temperature between 98 to 99, just one piece, then 98 to 99 to 99 to 100 degrees jump. Similarly, if you treat Markov chain as a sequence of random variables, that means x0, x1, that means it keep on going with a state space. But you see the state space is finite with the following properties. So xn equal to j, given x0 equal to i0, x1 equal to i1, xm minus 1, xm equal to I, which is equal to p, xn equal to j, xm equal to I for integer n greater than m. This is now our transition probability. That's what I'm saying. This mth time step to nth time step. The jump from m to n, the time steps, the transition from I to j. Pij. So this is written as Pij, m comma n, or just Pij. The same notation yesterday. So sequence of random variables. Again, coin toss example. Xn, we can keep on tossing the coins, infinitely many times. The state space remains the same, h comma t. but the sequence does matter. Suppose we conduct a coin toss experiment and measure the outcome of tosses for 10 times. It could be any number of times, it could be a larger number of times. And then the outcome of nth toss, n equal to 1 to 10, or it could be more. Sorry, this is a 10. Just replace this by 10. Then the s comma t, s comma t, is equal to h comma t. So the state space is h comma t, sequence of random variables, this is n equal to 1 to 10. You can measure as many, infinitely many times you can keep on tossing. Someone asking question?
So n should be starting from 1, I think, not from 0.
It is our choice. You can make it from x0. First toss, you can make it x0, initial value, or you can make it
last value will be 9, sir. If it will start from 0, then the last value will be 9, na?
Yeah, that's what. I mean, if you start from here, you can put 9, that's not a problem. I mean, you can put it as a 0, or you can remove 0, you can put it 1 to 10 or 1 to 9. Yeah, not a problem. Thank you. Either way, so you can have state space finitely, but you can keep on getting the outcomes infinitely. Keep on, continue experiment. So experiment could be conducted infinitely, like similarly random walk. If you have random walk, like the example of a gambler ruin in the 10 rupee example I gave, the state space is only finite. But a gambler may not come back, quit the gambling location. If the gambler gambler never loses, or he'll still have the rupees in his pocket, keep on playing. So this is another example I want to, maybe I take a break. Then I will continue this example, discrete time Markov chain. It's the example of the status of infinitely women. This is what the practical example for the infinitely status of a woman. This is what done with I have done some research on that area, so I can share that slide also on the article, real article also. Since we learned Markov chain, I want to show an application of the Markov chain. Maybe we'll meet after the break. So if you have any question on this particular lecture or previous lecture today or yesterday's lecture, we'll have a minute and we can.
So what is chain here in the Markov chain? Where is the chain?
The chain means it is the value of the random variable xn so on each time random variable picks, that depends only on the previous value. That is what it's called, a chain. Now that chain is English chain. It's not a sequence, it's not English sequence, but chain is here. English meaning of a chain. Chain is made with the joints.
All right. So it is not an ordered subset of a lattice kind of thing.
No, it's not that kind. It's not a lattice related chain.
All right. Yeah.
Just an English chain. So chain with some knots each time.
Fine, sir. Fine.
Any other question? Sorry, today you all have a long day. Already you have learned a tool from me and one from Dr. Edu, and you will have one more lecture. That ends after that. That ends the today's program, today's training program. Yeah. So we'll meet in. Dr. Edu, you want to say something?
Yes, there is one tutorial also today, 1 hour tutorial.
Yeah, after this, isn't it? After the
Yes,
break.
we can take break, sir. Yes.
Yeah, we take a break and then they also
Yes.
need to for me in the morning, but the kids, the students, especially they have in the evening time. It is a
Yes.
yeah. But I appreciate all of them. They are really taking it seriously, even though despite the evening hours.
Sir, can you suggest a small, thin book for the person who are not from the core mathematics side like me, who can understand this stuff in short span of time?
Sorry, I didn't. So you are asking the same. Are you the same person? I didn't see when I'm actually slides are shown. I can't see the name of the person. So you are asking the same who asked about the lattice.
Yes, 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 yes.
Okay, yeah, yeah. Well, you seem to be very attentive and asking a lot of sensible questions. I would like to suggest a advanced book to you. Do you mind for that,
Sir, I am from the computer science
or do you
background.
want an elementary book?
So my background is in
Computer science, yes.
so
Computer science, okay, good. No, you're asking very sensible questions, and of course, all of you are people. Some of you are sending messages to me. I could see it. So overall, everyone is following very carefully. But Goel ji, आपको मैं किताब अभी I'll write on the screen. Everyone can see the same book.
thank you, sir.
Sir, I also
Yeah.
want to. I also have some confusion.
हाँ बोलिए.
सर वो पी स्क्वायर आपने
Dr.
बताया
Gupta.
था कि पी स्क्वायर फॉर डिफरेंट डेज फॉर वन डे सेकेंड डे थर्ड डे बट व्हेन वी
हाँ.
मल्टीप्लाई पी with p square pq p3 there is not significant difference between the probabilities.
Correct.
Okay, then sir, for a COVID patient first day second day third day fourth day and after that वो रिकवर नहीं करेगा तो देर इज नो प्रोबेबिलिटी टू रिकवर तो आई थिंक इट इज
गुड क्वेश्चन. देखिए ये कॉइन टॉसिंग एग्जांपल हो गया या अदर थिंग्स, दे आर नॉट रियल वर्ल्ड. कॉइन टॉसिंग में जो न्यूमेरिकल वैल्यू कहाँ रखते हैं हम लोग वहाँ, दैट इज नीड नॉट बी ए रियल हॉस्पिटल बेसिक डेटा. अगर हॉस्पिटल वही दैट्स द यू आस्क अ गुड क्वेश्चन. सो आप कोर्स के बाद आप एक आर्टिकल लिखिए किसी हॉस्पिटल में जाके नियर बाय योर वेर एवर यू आर staying, you go to a doctor, you tell them that this is the course I learned. Now I want to test the things what I learned on the real data. Okay. And you go to the hospital, they will be happy to provide you the COVID data. आप उनको पूछिए, I want to build a stochastic model on that. I want to see the COVID patients with hypertension data. I want to compute the probability. अगर next time कोई COVID patient with hypertension आ गया, what is the probability of transition from COVID patient with hypertension recovery rate?
Okay, sir.
This is the purpose. That's the thing. You asked a very good question. This guy, all of you are asking very sensible questions. आप collaborate कीजिए. You go to a doctor who has the data, or you go to a hospital management. उनको दिखाए आपका certificate, आप trained stochastic modeler हो, and then you want to build. You want to help. This way, you are helping the community by having instead of getting an opinion about the various things, you show them compute. You compute and show them. This is the recovery rate of a COVID patient with hypertension. This is the recovery rate of a COVID patient with cancer. This is the recovery rate of a COVID patient with smoking. अलग-अलग probability आप compute कीजिए based on the either Markov chain or other things. Then you will see that the data and then you publish it.
Thank you, sir.
My pleasure. अभी मैं किताब लिखूंगा, एक मिनट. देखिए, lot of books are there. I think for the within India, the available books, Hindustan publishers, I don't know, red color books are there. In the publisher, they really written they published a very good book that is by Goswami and Rao. It's not me, but he was my teacher and former colleague. They both were teacher and colleagues, former colleagues. Introduction to process. And this is the book followed at Indian Statistical Institute, which I recommended on the screen. And number two, of course, Feller, you can read the by Wiley publisher. The first time writing publisher, Wiley publisher. Then the book by Feller. Part 2, William Feller. उनका है probability. Part 2. This is a penguin, I think, book. Fox. Many books are there, but first book I think it is for the Indian students, keeping in mind. I mean, this is very advanced. All three are advanced books, and they all start from the basics. Basics to advanced, they all go. One can read these books, and many books also there. Some of the books names I'm forgetting because I not recent times I have not referred because long ago I followed these books. But for regarding the GAN course, I prepared these notes myself. Yeah, these books are very good. D.R. Cox is one of the leading statistician. He died just a few weeks ago. He was at the age of 97. He is on like C.R. Rao, D.R. Cox, William Feller, Fisher, R.A. Fisher. They are all world famous statisticians. And C.R. Rao still alive. He's active at 101. He's 101 year old. Last year, before last year, we celebrated his centenary all over the world. In India itself, there are 500 conferences held. And David Cox also is 97, just died a few, I think 2 months ago, perhaps 6 to 7 weeks back, unfortunately. But he wrote a very classic book, Stochastic Process. Yeah.
So
that's why you get a refreshed. Otherwise, watching screen, long time is really. I don't understand, and I myself feel sleepy because I don't know, somehow Gyan program not sleepy. Usually, if I teach regular courses here, continuously watching screen and without seeing the students, I feel sleepy.
So I have ordered the first book just now, and it is quite cheap also. Of
how much it costs now?
360 rupees.
360, okay. Another book also there, I just look at my shelf. Lawler. This is also by CRC Press. Lawler. He's a very well-known probabilist. That is again introduction to same title, introduction to. Good. Yeah, all of you take a break. That's important. Get fresh up, and then we'll see in about 5 to 7 minutes.